3 and 4.
That's it. The velocity, thank you very much, is positive on the interval 0 to 1, union 3 to 4. Where is the velocity negative?
From 2 to 3?
Yes. 1 to 3. On 1 to 3. From this point, in other words, on the x-axis, till this point on the x-axis. So between x equals 1 and x equals 3, the velocity is negative. Perfect. Okay, let's see. Okay, when is each particle speeding up? So let's, okay, and what is it slowing down? Perfect. Okay, so let's analyze the graph. So we know the direction, right? So between 0 and 1, the particle goes this way. Between 1 and 3, it goes this way. And between 3 and 4, it goes this way. So that's already known. But where between 0 and 4 is speeding up? Speeding up, slowing down. So let's analyze what happens here. It starts with this velocity, and then still positive, and then this velocity, right? Because it's the slope of the tangent line. And then this velocity. What can you say between 0 and 1? Is it speeding up or is it slowing down?
It would be speeding up.
But it starts with something huge and then smaller slope and then smaller slope, and now the slope is 0. So the slope here is this, big, and then this, and then this, and then this, and then this, and then 0. We're talking about the velocity, but it's the same thing with the slope of the tangent line to the graph of the function. So what do we conclude between 0 and 1? What does it happen?
Slow down.
Yes, it is slowing down between 0 and 1. Okay, now let's continue. So it's positive, but slowing down. It starts with a big speed, but then in 1 second, the speed becomes 0. And now let's continue with this one. So here it starts with, and then I'll come back to that. So here it starts with a speed of 0. But now look at the tangent. Is it speeding up or slowing down between 3 and 4?
Speeding up.
Yes, because it starts with 0 and then increasing the speed, increasing the speed, increasing the speed, increasing the speed, increasing the speed. So between 3 and 4, it's speeding up. Now let's analyze what happens between 1 and 3. Yes, I know that the velocity is negative. We know that. But we want to know whether it's speeding up or slowing down. So it starts with 0 speed, and then a little bit steeper, and then a little bit steeper, till a certain point. I don't know if it's 2 for sure. Till a certain point, this is bigger speed. But then all of a sudden at this point, it starts lowering the speed to 0, back to 0. So here it starts at 0, increasing, 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 and then started decreasing, decreasing, decreasing to 0. So assuming between 1 and 2, the particle is speeding up from 0 slope to a bigger slope. But then at this point, it starts leveling off again to a 0 speed. So speeding up between 1 and 2. Union 3 and 4, but between 2 and 3, it's slowing down because from a higher speed, it drops to 0 again. So slowing down between 2 and 3. So this is based on everything we studied so far. All this analysis is based on what we studied in this chapter and the previous one. Okay, I would like to continue. Any questions for me before I say anything else? Anything else? Any questions for me here? Okay, more applications. So this is 3.9, related rates. We can spend on this section alone at least 1 month, and we still won't be able to exhaust it. So we're going to look at as many problems as we can. Okay, what does this mean? Just imagine I have a balloon and I pump air in the balloon. What happens? A lot. First of all, the radius increases. The volume increases. The area, the surface area, increases. All these are functions of time. Functions of time. And if I pump air in, they're all increasing. But they're not increasing at the same rate, right? But their rates will be related. Okay, what do I mean by that? So all increase, all are functions of time, and they will all, in this particular situation, when I pump air in the balloon, they will all be increasing. And their rates of change, dr over dt, dv over dt, ds over dt, are somewhat related through an equation. That's what we mean by related rates. Their magnitude, the rate of change, the magnitude of the rate of change are somewhat related. And they will be related through an equation. Okay, so let's choose. If we don't have the equation, we cannot determine anything. So this is 3.9, related rates. Okay, so let's start with something with the distance first, and then we'll come back to other examples. Okay, I'd like to start with 16, and then I'll go back and you choose. So we have at noon, we have a ship. It goes, okay, so at noon, ship A is 150 kilometers west of ship. Okay, so this is A, this is B, and this is 150 kilometers. Fine. A sailing east, okay, at 35 kilometers an hour. I'm just copying the information and then I'll stop sharing. And this one is going north at 25 kilometers per hour. How fast is the distance between the ships changing at 4 p.m.? Okay, that's all I needed. So now let's talk about it. So we're told that we have these two ships, and that happens at noon. So at noon, initially, they are to be found at a distance of 150 kilometers from each other. This is A and this is B. Then we know that A starts sailing this way and B starts sailing this way. And the speeds are given to us. This is the 25 kilometers an hour and this 35 and then 25. they're asking us to find the rate of change of the distance AB at 4 p.m. That's the question. So here's what happens. So here are my two ships, and they start doing this. And I don't know where, 4 hours from the moment they start, I don't know where, but I would like to be able to determine this distance between this and this. And not just that, I want to determine the rate of change of this distance. I don't care about the distance itself, but I want to know how fast is the distance changing exactly 4 hours after they start. So what do I have to do first? What do you think we should, after looking at this graph and understanding what's happening, this one is going this way and the other one that way. So I have to picture a particular instant. So I'm going to say that for me, A now is right here at an instant. I don't know where. I'm not interested in this. Not just yet. But I just picture in my head that at some point in time, A is here and B is up here. Why I need to do that? Because I have to picture that distance. And this is the distance in question, which I have to label. Give me any letter, but don't say D, because D is reserved for derivative. Just give me any other letter that you would like to use for the distance between A and B. Not time, because
C.
time is T. Which one? C, that's fine. C is fine. Perfect. Okay. So now you understand that at any point in time, forget about this, at any point in time, this is the distance covered by A. Let's label this as well. How do I label this? Since it's on the x-axis, let's label it
A of x. I mean, x of A.
just x.
X.
Good. So this one is going north. So this is the distance covered at any point in time by B. So since it's on the y-axis, let's call it
Y.
Let's call it y. Now I would like you to give me a relationship here. Where this is C, this is y. And can anyone...
we use basic geometry rules?
Thank you. But can anyone give us this piece, this leg, because this is a right triangle. Can anyone give us this piece? Knowing
150 minus x.
That's it. So now can anyone give us a relationship between the hypotenuse, this leg, and this leg? C, y, 150 minus x. I'm sorry, I forgot to say please. Anyone?
Can I take a guess on this one?
No, this is not there is no need for a guess. This is something we know since first grade.
There's a squared plus b squared equals c squared.
Careful. One leg squared plus the other leg squared equals the hypotenuse squared. Very good.
Or I forgot what it's called.
The Pythagorean
Pythagorean. Okay, yeah, that's it.
theorem.
Yeah.
That's fine. That's why we're here. But please, I understand that this is how we learned it, a squared plus b squared, but You have to be careful. The leg squared plus the other leg squared equals the longest side squared, which is the hypotenuse. Good. So this is 150 minus x squared, and this is y squared. Excellent. Good. So I have a relationship that involves c. That's what I want. I have an equation that involves c. What I'm really asked to determine is, one more time, the rate of change of the distance AB, whatever. Don't even think of this just yet. So how do I find the rate of change? What am I really asked to find, first of all? I have the function. We denoted it by c. You understand that these are three functions of time. X is not x, y is not y, c is not c. X is a function of time, y is a function of time, c is a function of time. They all change with time.
So we need to find a relationship of movement of B in correlation to movement of A.
Excellent. So, but the question is, find dc over dt. This is our question. When, but that comes into play a lot later, when t equals 4 hours. This is what we're asked, but do not even look at this. Do not put it anywhere before we find dc over dt. You cannot use this number till the very last step. Okay, so secondly, what is 35 kilometers per hour? What does this mean? And what is 25 kilometers per hour? What does this mean? Based on what we've studied so far.